So in the previous video, I talked about the version of Demoivre's theorem, which states that if z is re to the I theta, then raising it to a power is r to the n e to the I times n theta. And I think that makes sense when you understand that multiplying just rotates and that it will extend by r. And then there's this other idea, which is taking the root and how you can actually always get n distinct solutions when you take the nth root of a complex number. And so I'll start with the idea of a root of unity, and then I'll go on to talking about how you can do a root of any complex number and do it just sort of in general. So we'll look at a root of unity here. So for example, if I wanted to solve this equation, z to the n is equal to 1. That is equivalent to saying that z is the nth root of 1, right there. And I think it makes a little bit of sense to take a particular value, something like 8, and then look at what the different complex numbers are that are the eighth roots of 1. One of those complex numbers is pretty obvious, in the sense that anything is ever obvious in math. But if you take 1 and raise it to the eighth power, you're going to get 1. I hope it's also somewhat obvious that negative 1 to the eighth power will equal 1, because if you do an even power, then the negatives become positives. Slightly less obvious than that is positive I to the eighth power equals 1. You can realize that if I squared equals negative 1, and then if you have 4 groups of I squared, you're going to have 4 negatives that make positive 1. For the exact same logic, negative I is also a solution. But what I'm talking about are the 8 roots, so I should also have 4 other values on there. And this sort of suggests to me a circle with a radius of 1. And I would guess that this value, and this value, and this value are also roots of unity. And there's two ways to show it. One way is to actually work out in Cartesian coordinates this to the eighth power. Several different ways that you could do it. One way is to do the binomial expansion and write out all the coefficients and cancel everything out. If you want, you can do that. I actually do suggest you do it once in your lifetime and only once. But a nicer way to do it is just to square it and then take your result to the fourth power. So if I square this, I guess I left off my I. There we go. If I square this, I have root 2 over 2 plus root 2 over 2i times itself. And then I'm going to take that result up to the fourth power. This right there makes 2 over 4. Then we have 2 copies of 2 over 4i. And then we have this, which is 2 over 4i squared. And that result is all going to get raised to the fourth power. So 2 over 4 is the same as a half, and I squared is the same as negative 1. So I have a half minus a half. And here I have 2 times a half. So all that I just have left over is the letter I raised to the fourth power, and we already explained how that equals 1. So I've proved to you so far that there is 1, 2, 3 solutions. I haven't proved to you that this one is also a solution, but if you just go through the same steps here and make the x coordinate negative, you will see that everything works out the same way, just with a negative in the middle there, which makes a negative I to the fourth, which also equals 1. So we know this is a root. We know this is a root. This one down here, if you do this to the second power, it will get you back to positive I. If you see how I'm following the negatives through here, we have a double negative, and it makes it positive I. So that's a root. That's a root. This one comes out to be negative I. So the point is that when you have the nth root of 1, your other roots are spaced evenly around the unit circle. And the entire rotation of the unit circle is a rotation of 2 pi. So the way you can find all of your roots is like this. You start with the principal root, which is just 1 by itself. And the value of 1 has an angle of 0. So you start with your angle of 0. And then you add rotations of the circle divided by 8. But you don't just have one answer, you have 8 different answers. And so we just use the letter K as an index. It's just counting, K for counting, of course. It's just counting the number of solutions. So we just write that it's an integer. Sometimes books will go out and spell out that K equals 0, 1, 2, 3, 4, 5, 6, 7. You could also count from 1 to 8 if you don't like counting from 0 to 7. You could also write any number of integers if you don't mind there being repeated solutions. Because of course, once k gets to 8, 9, 10, etc., you're just going to rotate back around the circle again. So this is the idea for a root of unity. A root of unity is on the unit circle, and they're all evenly spaced out by rotating by 2 pi over n for whatever n value you have. So if you had, I guess I did my particular example in terms of 8. The general example would just replace the letter 8, the number 8, with the letter n. Now, if we want to generalize this even a little bit more, we can have an arbitrary complex number, such as re to the I theta, and then I'm claiming that the nth root of z is the nth root of r times e to the I times theta plus 2 pi k over n. And here's the proof. If I take that expression on the bottom, this one right here, and if I raise this all to the nth power, what can I do? Well, when you raise a multiplicative expression to the nth power, you can distribute that. So I have the nth root of r raised to the n, and I have all of this other stuff also raised to the n. When you have a power raised to a power, you can multiply those two powers right there. So here we have the nth root canceling out with the nth power, and here we have multiplying by n canceling out with dividing by n. So what we have left over then is r e to the I times theta plus 2 pi k. And this equals re to the I theta for any k that is an integer. Anytime the k is an integer, you're just rotating a full circle, so you're back at where you started. So just to finish up this video with a quick example, let's say for some reason they ask me to solve z to the 6th is equal to negative square root of 2 over 2 plus root 2 over 2i. What I'm going to do is find that value. It's something like this. I'm going to find the theta. I'm going to find the r. And so the r you find by doing the square root of the x coordinate squared plus the y coordinate squared. I guess I could have chosen a different example. I just chose another example from the unit circle. Oh well. It's the same exact process regardless of what your r is. So you get r equals 1. Your theta value is going to be the inverse tangent of the y coordinate over the x coordinate, except we are in quadrant 2, so I'm going to add pi to that. If I do that, I would get 3 pi over 4. And so then I know that all of my 6 z values would be of this form right here. They would be the 6th root of 1, which is still just 1, times e to the I times my original theta, 3 pi over 4, plus 2 pi k, all divided by 6. And if I wanted to explicitly write those, I would just go through the 6 values of k, starting with 0 and ending with 5. So like z uh, 0 would just be e to the I times 3 pi over 4. Z1 would just be e to the I. I'm sorry, did I say 3 pi over 4? I should have divided by 6, so 3 pi over 24. The next one, I'm going to add 2 pi k to that. So that's 11 pi over 4, 11 pi over 24. So Z2, I'm going to have e to the I. I'm adding 4 pi, which is like 16 over 4. So we have, 19 pi over 24. Z3 is e to the I. So if k equals 3, I'm adding 6 pi. That's 24 over 4. So that's 27 pi over 24. Almost done. Z4 would be adding another 8 pi over 4. So we get I times 35 pi over 24. Z5, the last one, e to the I times 43 pi over 24. And it may not be obvious, but if I added one more copy of 2 pi, it would get me back to this original value, because adding another 8 to 43 gets you to 51, and 51 pi over 24 is the same as 3 pi over 24 if you subtract a full circle, which is 48 over 24. So that's the idea behind de Moivre's theorem used for finding roots, is that you can rotate full circles and end up at the same place. And so if you put that idea together, you can now find the root of any complex number.